from the audience about a problem that they had trouble with, and we'll do that one.
Number 3.
Number 3, 1.3. Okay. 1.3, it says a solution of volume 50 cubic centimeters contains 2 times 10 to the minus 3 molar iron 3 plus and 1 times 10 to the minus 3 molar tin 4 and 1 molar hydrochloric acid. Basically, it's asking you've got a rotating disc electrode, has mass transfer coefficients. Calculate the limiting current for the reduction of iron 3 under these conditions. Okay. All right, so number A basically is using the equation that we've already derived. And so the limiting current for iron 3 plus basically would be the reductive current. So it would be the cathodic branch of that system. Now in this case we can use the derived limiting current form for a single species present in solution. So remember we derived the current potential curves in our semi-empirical treatment for a single species present in solution, oxidized species present in solution. We don't have iron 2 present initially in solution, so we can use the simplest form of that equation. And so that's equal to, as I remember, it's m sub 0 NFA C 0 star, right? So all we have to do is then put in our all the relevant parameters. What's the mass transfer coefficient?
10 to the minus 2.
10 to the minus 2 centimeters per second, right? Iron 3 plus is going to iron 2 plus, so N is equal to 1 in that system. F is 96,485. That's how I always remember it. So that's coulombs, basically per mole of electrons. And A is given, right?
0.3 centimeters squared.
0.3 centimeters squared. Where you might have some trouble now is if you do the units, you'll see that we've got units of cubic centimeters in the system. And so what we actually need to do is put in for bulk concentration, not the molar concentration, but the concentration in moles per cubic centimeter. Okay? Rather than moles per liter, we need moles per cubic centimeter. So that's kind of the tricky thing about the bulk concentration, especially in these electrochemical problems. So C sub 0 star is the concentration of iron 3 plus, which was 2 times 10 to the minus 3 moles per liter. But if you do the math, you'll see that it's 2 times 10 to the minus 3 moles, 2 times 10 to the 6 moles per cubic centimeter. There's a factor of 10 to the third in that system.
Part B of the problem.
Okay. Yeah, okay, so that would be the thing. Actually, the answer then is 5.79 times 10 to the minus 4 amps. And then you could do the 10 the same way. Part B is current potential scan from plus 1.3 to minus 0.4 under the above conditions. Make a labeled quantitatively correct sketch. Okay. So basically it's asking you to take the given concentrations and potentials that you'll have to get from the back of the book, and assuming we've got mass transfer controlled reactions and Nernstian reactions, make a labeled correct thing. So what we'll have is a sketch, something like this, where here is E. Again, we're going more negative in this particular direction. And we start out, I guess we're probably, let me start over again. Most of our interest is over here on this side of the graph. So E again is negative. I, cathodic, is always up in this book. not always in the literature, but in this book it is. Well, we can write, I won't be able to draw it exactly right, but first of all, we can think about perhaps having a little bit of a curve here for oxygen. That doesn't really say anything about it, but that would be oxygen oxidation, oxygen production, I should say, by water oxidation. Then if we go to about 0.77 volts, we'll see a curve like so, and that will be, and that's going to be the iron 3 plus 2 plus couple, all right? And the important thing to think about there is that the half-wave potential will be the E0, and that's true because of it's a Nernstian equation, it's a reversible equation. So in that case, the E1/2 is equal to E0, and that's 0.58 milliamp. Then for the tin, the E0 is plus 0.15, and it turns out that the wave is a little bit higher, 1.2 milliamp. For the tin 4, SN4 plus to SN3 plus. And then almost immediately we'd get some reduction of protons in that system. So, but that would be about right for the sketch. So we've used the semi-empirical current voltage curve formula for a Nernstian process with only the oxidant present initially, or the oxidized species present initially, and we get the limiting currents for both processes. Notice they're cumulative. The limiting current for the tin 4 plus is on top of the limiting current for the iron 3 plus. Now those curves would look different if we had both iron 3 and iron 2 in solution, or if we had tin 3 and tin 4 in solution. Okay.
So we can use the equation that you use in problem A.
Mm-hmm. Right, that, if you'll notice, this current here is 0.58 milliamps, and that's the current we would sketch on the graph.
My question is, if we can use the equation 1.416 of the book,
Mm-hmm.
and find the limiting current of iron and the limiting current of tin, and use that equation to make the sketch of I versus E.
Yeah, you could actually plot it based on that equation to get an exact plot. Okay. In this case, the question basically said sketch a plot. So usually when they say sketch, they don't say do an exact plot. But yeah, you could actually put that into a program. And actually, you can't. It's hard to do it because you have to do it kind of you have to solve it numerically. 1.416. And that plot would give you the proper shape of the curve, particularly for the iron 3 plus species. For the tin, then if you wanted to use that, you would have to take that same current and just add it directly on top of what you already had for the limiting current for the iron 3 plus. So you could use that curve, but you'd basically have to add those two plots together. Okay? Right, you can do that. I guess the main thing I would think about in a sketch is having the E1/2 at the right position and the right limiting current. And basically the shape, but an exact plot is not necessary when I say sketch.
What is the limiting current in the second case for the?
1.2 milliamps.
What did you get this learn? They have nearly everything the same. Like the only difference is that with 2 electrons.
The limiting current for the tin is the same as the limiting current for the iron.
No.
Maybe.
They differ in the concentration, but like one is double the concentration. Iron is 3 is double the concentration of tin 2, tin 4, But tin-4 has 2 electrons.
Oh yeah, you're right, I've messed that up, so. Yeah, in that case, that'd be the same.
Yeah, what if we do this like cycle, instead of scanning only one, or just reverse the scan? What will be the shape of this?
Reversing the scan at what point? Here?
Started at 1.2 until -0.4. If we reverse from -0.4 and go back.
Well, this is a little bit hard to say because in this particular case, since it's a rotating disc electrode, we would expect to retrace exactly the curve out and back. Because it's at what they call steady state, the current is not dependent on time. So, and it also really doesn't depend on in principle, it doesn't depend exactly on the previous state of the system, because if we scan sufficiently slowly, it didn't really matter if we arrived here at this point from starting here or if we came back from some other point. So these are steady state curves and they would have the exact same shape going forward or backwards. As you know, and other people will find out, that's not normally true. Normally we don't have what they call steady state curves, and the shape of the curve on the forward and the reverse sweep would be quite different. But in this particular case, they would be the same.
So you have almost a straight line between the two?
Now, if we swept out, we'd get this shape, and then if we swept back, we'd basically retrace the curves.
All right, so it goes back up when you get into the height.
Right.
It starts going up.
Sure.
Okay.
The only thing is that it does depend on potential and actuality, because if we get out here, we're starting to reduce hydrogen ions or making hydrogen gas. That stirs up the solution. Not such a critical deal, but it also changes the pH of the solution, which will affect the potentials of the tin and the iron. And so depending on how fast you sweep back, you'll see those effects as well. Depending on how much the solution is buffered, you'll see those effects as well. So in practice, doing this sweeping out and back, you won't see an exact duplication of the shape of the wave on the forward and the reverse sweep, but be pretty close. Okay. Well, we've got some time, probably time for one more question. Is there anyone that?
For question number 1.
Mm-hmm.
How do you determine the potential of the electrode itself? The potential at which the current is 0, the equilibrium potential.
So in 1, I don't know if that's what's asking you, but is that what you want to know?
For instance, for number A,
Yeah.
or just we got a group of like possibility for the reduction and for the oxidation.
Mm-hmm.
According to the book, he doesn't show us how he determined the level of the potential
Mm-hmm.
of the platinum or the mercury electrode at which there is 0 current.
Yeah. Well, in this particular case, it's not directly apparent, but if you examine it, you can ask yourself, if I'm at certain potentials, I will have a non-zero current flow. For example, if I'm at sufficiently negative potentials, I will have copper reduction from copper 2+ to copper metal. Is that right? Likewise, if we'll have a cadmium reduction to cadmium metal. So there is a potential which has to be more positive than the reduction potential for copper and cadmium to avoid that possibility. Likewise, in this case, it's a platinum electrode, so we have to be more positive than the hydrogen ion reduction potential as well. Right? So you can write down all of the particular, for 1.1a, you can write down all the equations, the chemical equations for electrochemical processes that can occur. For example, copper 2+ plus 2 electrons goes to copper metal, and that's 0.34 volts. Cadmium 2+, plus 2 electrons going to cadmium metal, is minus 0.403. Hydrogen ion plus an electron going to hydrogen gas, 0 volts. Are the basic ideas. There are a number of other possibilities. For example, we can think about the reduction of water. That would be water reduction going to hydrogen gas plus hydroxide ions, and that occurs at about minus 0.8 volts. We also have the possibility of oxygen production, or oxygen, the reduction of oxygen, but that would be given basically by the following equation where we oxidize water to form oxygen. That E0 is about 1.23. Actually, there is a platinum oxidation potential. Okay, also at about probably 1.2 volts. So the question is, where would we be? We have to be at a place where there's 0 current, okay? We can't be any more negative than 0.34 volts, because at that point we would be reducing copper ion to copper metal. And that takes into account, then we don't have to worry about cadmium or hydrogen, because both of those are already more negative than that. So as long as we're more positive than 0.34 volts, we're okay. And for on the other side of the area, you would have to be at least as negative, or at least as positive as 1.2 volts in order, before we'd see, so for example, platinum being oxidized to platinum ion, or water being oxidized to oxygen gas. So the electrode would be somewhere between 0.34 volts and 1.2 volts. In any of that range of potentials will have 0 current, and that would be a potential where we could possibly have the electrode at a potential. So that would be basically the equilibrium potential for that system. Now, if we go negative from the equilibrium potential, the first reaction would be copper reduction, and we go positive, the first reaction would be or platinum oxidation or water oxidation, one or the other. Both platinum oxidation and water oxidation are not a very kinetically rapid process, so it's hard to suggest which one would be first. It would depend on the particular system. Probably platinum oxidation, though.
All right, so you could use these that are on the back cover of the book.
Yeah, yeah.
Equilibrium potential.
Right. Remember, those are just equilibrium potentials. They don't actually have any kinetic information about it. So.
But those are against the normal hydrogen, standard hydrogen.
Yeah.
So I have to transfer to the Kalman electrode. I did it just by subtracting the potentials, right?
Right. These are, yeah, and that's.
Is that right?
These are all versus normal hydrogen electrodes, I guess. That's what I wrote down. Is that right?
Yeah.
Well, just like I mentioned today, we can convert from one reference potential to the other simply by subtracting off the calomel electrode potential. So for example, the copper potential is 0.34 volts. The SCE potential is about 0.24 volts. So the difference between is 0.34 between the NHE, 0 point, but it's only about 0.1 volt versus the for the SCE potential. Okay, so here's our curve, and again, so the difference between these two potentials is only about 1/10 of a volt. So.
There is another possibility for the sulfate ions to be oxidized to pure sulfate.
Mhm.
This one, right, or you don't take this into consideration because of the size of the ion.
What's the potential for that?
This one is 2.26 volt versus normal hydrogen.
Yeah, well, that's point plus 2 volts, and so, yeah, you could continue to write possibilities, and so, but that's not going to happen because the first reaction would be either platinum or oxygen, not the sulfate oxidation. So changing, like I said, changing to different reference potentials. You're saying subtract. That works, but you can always write half cells and figure out exactly how to do that. Is there any other one?
Yes, sir. Problem 1.4 A says calculate the resistance between two parallel planar platinum electrodes of 0.1 square centimeters area.
Mm-hmm.
Place 3 centimeters apart in the solution. What I did was I used the formula that is X divided by kappa
Yeah.
I the area. But well, that's supposed to be for a tip electrode, for an electrode approaching.
Well, this would be appropriate for the uncompensated resistance or the solution resistance. Either way, is it's for a particular type of calculation where you would have two parallel plates separated by a particular distance. Let's call it X, and then each plate would have a given area, and that would be a simple. And that would assuming basically there's just a cylinder of solution between those two plates, and no current would be outside that cylinder. And yeah, you can use that particular equation. That should give you the right answer.
So there is always assumed that the two plates or the two electrodes have the same area.
In this case, we have to assume, for this particular equation to be correct, we'd have to assume those plates have the same area. Right.
Because I was thinking of if I had to multiply the area by 2 because I have
No.
one,
No.
only one. No, I don't.
No. Because really what you're thinking about is not the area of the plates total, but just the area that the current flows through. So you're thinking about a tube essentially here. Okay? So the current flows through that given tube of the solution. Then they're talking about repeat the calculation, well, putting it at a different distance apart. Now, what they've essentially assumed, or make the assumption, is that since the resistance along that tube is probably going to be a linear function of the distance. So in other words, you can think about it as a physical resistor across that, and anywhere you put the thing along that, it'll just be like a variable resistor, if you will, and you can adjust it to different points. There's a different calculation for a spherical electrode.
But one thing we were saying, in parts B and C, it is assumed that a very large counter electrode is deployed.
Right. In A, because of the geometry, we're assuming two parallel plates together. In B and C, it's often the case that we don't have a situation, especially in electrochemistry like this. Now, conductivity measurements, where you're measuring the conductance of a solution, this would be exactly the situation. But in electrochemical experiments where you're trying to do an experiment, that's often not the case. Usually you have a very small electrode compared to a much larger distance away counter electrode, perhaps a coil of wire or a screen of some sort. The calculations for the the equations for the uncompensated resistance in the spherical electrode case are assuming that particular geometry, that you've got essentially a spherical electrode that is surrounded at some infinite distance by a spherical counterelectrode. Okay? In other words, you've got an electrode and then completely surrounding it, you've got at some infinite distance away, full of solution between those 2 points, another electrode. Okay? So in practice, that's the theory, but in practice it turns out that it doesn't necessarily have to be infinitely large or infinitely far away to approach it very closely, that particular case. And so as long as it's sufficiently far away and sufficiently big, it doesn't matter whether it's infinitely large or infinitely far away. The derivation that you've got in the book is assuming that you have an infinitely large, infinitely far away counterelectrode. But so then you use a different form of that equation, 4 pi kappa R0, and then x plus R0. Now in this case, what happens if x is infinite? This part of the equation goes to 1, correct? So the derivation assumes that you can have at various distance here, but if x is very large, this goes to 1. So that's basically how you solve that. I guess it doesn't. I'm sorry. I didn't. That's not exactly what the question is asking. You can put in different values of x to get different values of the resistance. But the reason they're saying very large counterelectrode is because that's the derivation, is assuming a large counterelectrode. Well, we're basically out of time, so why don't we stop here? We didn't get to the paper, so we'll just leave that paper for next time. We'll discuss the paper next time.